Hello, everybody. Welcome back to our video. We have here a specific graph which we'll begin to perform today, the Dijkstra'S algorithm. When we say Dijkstra'S algorithm, we wanted to get the shortest path um, in our specific graph. So what we can do right now so that it will be basic for everybody, we have to create excuse me, a table wherein mhm, we have here a table for all of the nodes. And take note, by the way, since Dijkstra's algorithm, just wanted to let you know that this is actually not does not allow to have any I mean does not allow any negative value. So therefore, Dijkstra's algorithm will handle positive value only. So we have here a specific data from A to J. When we will begin to check in your maps, by the way, if you're trying to check it or apply this into geo mapping, shortest path is really useful because once you will begin to, if you can consider from town A down to town G, what will be the shortest path? You can do it like that. So right now we will do the from your node A, since that is the start state that we do have, all of the specific nodes will be relaxed. That is relaxation. When we say relaxation, assumed that they are having infinite value. And our goal is to change that infinite value down to the shortest data. So we'll begin to visualize that step by step on how can we perform or how can we optimize the data right there, since of course we have to make sure that everything might um be resolved right there, since this is really very useful in terms of the implementations. You need to really be aware of the step by step process regarding in this features. Okay, now let's go ahead and take it one by one, since I don't want you to really be um I don't want you to overthink the process. So in this case class, we have to check from adjacent to adjacent, since in our Dijkstra's algorithm, it must be searched um from the specific data, I mean start state, I mean, and then up until the very um up until the all nodes, I mean. You have to check all the data, all the nodes. What will be the value? What will be the minimum or the shortest value that we can do? Okay, considering that the node A will be, this is for the step one, or the first iteration, we can say that is infinite. That we will set them into infinity, into infinite value. And our goal is to change this into a finite value wherein shortest value. Okay. Now, what will be the adjacent of A? The adjacent of A, and once we will have a value class, please do make sure that you will begin to um since if you'll update that one that is that has been marked as visited, so therefore we'll do it like that. So this graph is a directed graph, because in an undirected graph that is bidirectional, it will be hard for you to implement. So considering the fact that you're studying from AVL3 down to the sorting technique, so we have to lessen the time also. I mean, make sure that you can answer this in just a time frame of 2 hours and 30 minutes, considering that this is really so simple. Now, how to work on this? Since everything is relaxed in our algorithm, so we have here from A, there will be a what they call this one, the predecessor, I mean successor, which will be B, G, and F and E. So from there, 0 plus B, going to B is 6. So therefore 0 plus 6 is better. That's gonna be 6. Then you have to cancel out this infinite value. So what we can do, B will become 6, and the infinite value, you will begin to cancel that out, since 6 is the shortest value than the infinite value. Okay, because that's our goal actually. We need to um optimize the value here. Okay. What will be the other adjacent of A? There will be G. Going to G, there will be 3. So 0 plus 3, it will become 3. So therefore, 3 will is better. So therefore, you have to cancel that out, the infinite value. So G will become 3 right now. Then cancel this. Okay. Now you have another adjacent, which is the F. F is 0 plus 5. So therefore, cancel that infinite, and we will begin to change that into 5. The same into your table, so that you can definitely understand it better, class. Might be good if you have, if you're tracking that here in your table, so that you can understand it clearly then. Now, in your E adjacent, there will be two values. So therefore, you can just change that one into two, and then cancel that out, the infinite value. So therefore, it will become two. Now, we're done with those particular node, E, F, G, and then B. Now, you will be going to check actually the neighbors of those visited list. So what will be those visited list that you do have? So better class, if might that you will keep on the tracking that. So in your first iteration, in the first step of your first iteration, um since that is the step one, then the first iteration, you were able to visit A, B, mm, F, no, 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 E, F, E, F, G. Now, it could be like that. You will begin to visit, or you're done visiting the neighbors of A. So we will proceed with the neighbors of B right now. From there, what will be the neighbors of B? This will be in your second iteration, okay? Visiting B. So what will be the since your B is having 6, okay? Now going to the value of um going to the node C, there will be a 9 value, a weighted value of 9. So therefore, 6 plus 9, it will become 15. So node C is actually having infinite value. So therefore, cancel the infinite value, and then change that into 15. So since 15 is actually much more optimized than 15. Okay. I mean the than infinite. The infinite value. I'm sorry for that. Okay. Now the other adjacent of 6, or B, I mean, will be G. So going to G, 6 plus 8. So it will become 14. So since earlier we're able to have there number 3, so therefore 14 might what do you call this one, it's not optimized since 3 is better than 14, so therefore you will not be going to change the value of 3 into 14, so therefore you just have to cancel the 14 and then stay there 3. Okay, now um for letter B, you're done visiting letter B in your first iteration. Now, okay, let's finish this first. In your first iteration, visit EFG. Now check the E. What will be the adjacent of E? The adjacent of E is actually F alone. Then there will be two value earlier. 2 plus going to F is 7. So 2 plus 7 is 9. So your F do have a value of 5 earlier. So therefore, 9 will not be going to change the value of your F, considering that the value of F right now is short. I mean, it's already 5. So 5 is better than 9. So therefore, choose 5. Okay, now we're done with letter E. Let's proceed with letter F. Letter F adjacent is G and I. Now, from letter F, we have 5 value. Then going to G, there will be 6. And 5 plus 6, that is 11. So therefore, assessing the value right there, which your G is having 3 value, is what we have encountered earlier. So therefore, 11 is not better. So 3 will still be the value in your node G. After that, since you were able to visit a letter um, G, you'll go with F. So from F, you have the value of 5 from F, and then going to the I, there will be 4. So 5 plus 4, it will become 9. So you have to cancel the infinite value, so it will become 9 for your I. Okay, you're done with that. Okay. Now, since we are actually finished in terms of F, since there will be two adjacent, you have to proceed with letter G. Considering that your letter G, you have 3 value. And what will be the adjacent of your letter G? The adjacent of G is I and J. So therefore, from letter G going to I, there will be 90. 3 plus 90 will become 93. So considering that your I were able to check earlier the shortest value, which will be 9. So therefore, 93 is worst. We will cancel that out and chose 9, since that is more um optimized than the value of 93. Now, we're done assessing the letter I. We'll proceed to J node from G. So 3 plus 17, so therefore it will become 20. So since considering that your J right now is actually um, infinite, it is infinite, so therefore you have to cancel the infinite value for letter J, and it will become 20. Okay, that's how you will work on that. So in your first iteration, you were able to visit A, B, E, F, G. And then in your second iteration, you have been able to successfully search aside from A, B, E, F, G. You were able to update I and J, right? So therefore, here, what we're gonna do, we will begin to visit the also C has been updated earlier. So therefore, will become CIJ. All right. So we have to visit the nearest or the neighbors of the C, I, and J to make it more optimized. Okay. And after this is actually the second iteration in your step one. And we will begin to recheck later on if this value that we were able to find in our step two, just to recheck if our value is really good, just to make sure that it is really the shortest path values. Okay. Now, since considering that A, B, E, F, G has been visited, excuse me, earlier, let me just pause. Okay, so considering that we're able to visit earlier the nodes for A, B, E, F, G, so let's actually proceed to C, then I, and J. Okay, now what will be the value of your C right now? What will be the adjacent of C? C is actually having four adjacent, which will be G, J, H, and D. So from C, there will be a 15 value. Now let's try to assess the neighbors for that. 15 going to D, there will be 30 value. So 15 plus 30, it's gonna be 45. So therefore, D is actually infinite, so therefore we can update that one into 45 since infinite is um not good. So let me just go ahead and keep on tracking that here also, that we're able to visit already D and it has been updated so that we will not be going to be lost in our calculation. So since we're able to finish the letter D, from letter C going to H, there will be 26. So therefore, 15 plus 26. So that's gonna be 41. So 41 is better than infinite. So therefore, cancel infinite value, and um it will become 41. Okay. Now keep on tracking the iterations value then. And we have here from C going to J, there will be 21. So from that path, going to that path, I mean 15 plus 21, it will become 36. Considering that your letter J earlier is, we're able to calculate that into 20. So therefore, we will not choose 36 since 20 is better. Okay. Now, well, there will be 15 from letter C going to G, 71. So 15 plus 71, it will be 86. So therefore, what you will gonna do, 86 is not good than 3. So therefore, in your letter G, it will become still 3. Okay? Now, after that, we're able to visit letter C. Let's continue with letter I. Assessing I, what will be the adjacent of I? Adjacent of I is only J. Then from I, there will be a value of 9. Then going to J, there will be a value of 52 for the path. So it will become 61. So considering that you have for letter J, it will be 20 already earlier. So therefore, you will not choose 61 because that is not the shortest value. So we have 20, we'll keep as that. Okay. Now you're done visiting letter I because it's having only one adjacent. So what we're gonna do right now, you will visit letter J. J don't have any adjacent, so therefore you'll keep as is. So considering that you were able to visit A, B, E, F, G, C, I, J, we'll visit letter D and H for the adjacent. Now, from letter D, what will be the adjacent of letter D? That will be H alone. So from letter D going to H, there will be 45. So 45 plus 45, it will become 90. So therefore, You already do have a value of h earlier as 41. You will not choose the 90 since 41 is better than 90. Now we're able to visit letter D right now that has been visited, and you will check also the adjacent of H. Adjacent of H is actually the letter J alone. So 41 is the value of your letter H. Going to the J, it is 81, so 122. Considering that we have 20 right there in your letter J, it will be better. So you will not be going to update. It will still be as 20. So that is, we're able to visit earlier all of the nodes that has been visited. That's for the step one. Now in your step two, you just have to recheck if everything is if everything is really optimized. Okay, you just have to recheck actually the value. So from A, there will be two that is good. So 0, 6, 15, 45, 2, 5, 3, 41, 9, and 20. We'll just check if there will be some updates that we can do or perform later on. Okay. Now, what will be this for the step two? The same iteration, you will use that one. In your A, the adjacent of A is B, that will be 6. There's no update. G, 3, that's still good. So 6 is good na. B, 6, okay na siya. G, we have for letter G as 3, that's good. Then F will be 5, so that is better. And A to E is a 2, that is still 2, that's good. Then after that, the adjacent of the same thing, we're able to visit A, B, E, F, G. Then we'll visit right now the letter B. Adjacent of B, 6 plus 9, still 15. So therefore, C is maintaining 15. That's good already. Then 6 plus 8, it's gonna be 14. So 14 is actually not optimized. We have 3 right there, so that is better. After that, you will begin to visit the letter E still. For letter E, you have 2 plus 7, it will become 9. So 5 is better, so therefore there's no changes. Then afterwards, you visit node F. So since we're able to visit E, F is adjacent to G and I. From F, there will be 5 plus 6, 11. So that's not good. From F going to I, 5 plus 4, it will become 9. So as is. So therefore, it is optimized. And we're able to visit F. We'll go to G. G is having the value of 3 plus going to I, 9 plus 90 plus 3, that is 93. So that's not better. Okay. No, for your I, it will still be 9. And then 3 plus 17 will come 20. So J will become 20. That's better. Then you were able to visit A, B, E, F, G. You will begin to assess right now the CIG, since you were able to visit those particular states right earlier. For your C, you have adjacent of 4 adjacencies. So 15 plus 30, so 45, so that is better. So you just have to keep as is. And then 15 plus 26, so since you have there in your H, 15 plus 26, so it will be 41. So 41 will be better. So you just have to maintain that value. And then from C going to J, 15 plus 21, so 36. So 20 is better. So you don't have to update. Then from C going to G, there will be 15 plus 71. So therefore 86. 86 is not good because 3 is better. Then you just have to keep as is, and then we're able to visit everything. And then you'll proceed with I. What will be the adjacent of I? I is actually adjacent to J. You have 9 plus 52, so therefore it will become 61. 61 is not good than 20, so therefore maintain 20. Then J don't have any adjacent, so that has been considered as visited. So in your step right now, you have to check D and H. What will be the adjacent of D? Adjacent of D is for H alone. So 45 plus 45, it will become 90. So 90 is not good. Then 41, 41 still remain as is. So from H, what will be the adjacent of H? That is J. So from H, that is 41 plus 81. So therefore, 120 to 122 is not good. 20 is better. So therefore, this will be your final shortest path. Now you have to calculate according to the value that you do have, or the shortest value that you do have, accumulating everything. So therefore, what we're gonna do, sorry, let me just write it clearly because it might confuse you, okay? Now you have to calculate the shortest path for the Dijkstra's algorithm. What will be the total value? So you have you 0 plus 6, 6 plus 15 plus 45 plus 2 plus 5 plus 3 plus 41 plus 9 plus 20. So therefore, it's gonna be 146. So from this operation, our value, or the shortest path value for all of the states accumulating is 146. So therefore, if you will go to A, um, I mean go to B from A, there will be a shortest path, 6, 3, 5, 2. That's actually, this is how the process work actually, class. So hopefully that you were able to learn something about the Dijkstra's algorithm, and make sure to understand it clearly, because this will really confuse you if ever that you were not able to understand it well. You can just rewatch or pause the video, and of course try to check, or you can definitely ask me as well if ever that you do have you're having a hard time. Thank you so much, everybody, and see you in the next video, as I'll begin to illustrate also the Bellman-Ford algorithm, since Bellman-Ford algorithm will definitely accept value of negative value then. Thank you so much, everyone, and goodbye.